Yes.
Yes, it's a pleasure to be in this meeting today. I'm going to talk about the feasibility of using manganese nanoparticles for magnetic hyperthermia. Hyperthermia refers to the increase in temperature above normal levels between approximately 36.
Sorry, Sam, I think, sorry. I think there is an image near to your, in the right side of your presentation that is blocking your presentation in the right side.
This one?
No, in the right.
Ah.
Yes,
Okay.
maybe if you, yeah, okay, that's okay.
Okay. Okay, it's better now, I guess. I was saying that hyperthermia refers to the increase in temperature. Hyperthermia, the concept of hyperthermia refers to the increase in temperature above normal levels, but in the other hand, the hyperthermia as a treatment refers to a localized increase in temperature in the range of 41 to 46 Celsius degree in an area of interest that could cause in an organism a direct cytotoxic effect or act as an adjuvant to other treatments such as radiotherapy and chemotherapy. In particular, magnetic fluid hyperthermia is based on the use of magnetic nanoparticles to reach these temperatures through the absorption of energy from an alternating magnetic field. As an example, in this figure, I illustrate a coil that by passing a current induces a magnetic field. Inside that coil is a mouse with magnetic nanoparticles that have been internalized and directed towards the region of interest, and the treatment will consist of a localized increase in temperature. To determine the heating efficiency of nanoparticles, we use a specific absorption of power, defined as the power dissipated per unit mass of the material. The power absorption depends on intrinsic parameters of the magnetic nanoparticles, such as the size, the composition, the effective anisotropy, magnetic saturation, and also of characteristics of the experimental setup and the medium in which they are found, such as the frequency and strength of the magnetic field and the viscosity of the medium. Bearing this in mind, there is an optimal combination of the parameters for which the power absorption is maximum. This plot illustrates the heating rate as a function of radius for different applied fields, but with all other parameters fixed. We see how, in this condition, there is an optimal radius for which the power absorption is maximum, and above or below this value, the power absorption decreases. For this case, we use the manganese ferrites because they present one of the smallest anisotropies among the ferrites. Thus, we examine two systems of manganese ferrites and evaluated the heating efficiency. For the synthesis, we use the method of thermal decomposition of organometallic compounds in organic solvent and assisted by surfactants. From the synthesis, we obtained two magnetic systems. The first thing we did was transition electron microscopy analysis to determine the size. In these figures, I show you two representative 10 micrographs of the samples. We analyzed several micrographs using IMageJ and performed size statistics for finally fitting a log normal distribution. From this, we obtain a mean diameter of 12 nanometers and 28 nanometers. And with high resolution 10, we can appreciate in greater detail these synthesized nanoparticles, where we find plane structures associated with the crystalline structure of the particles. To find out the elements that make up the particles, we perform energy dispersive X-ray spectroscopy using a scanning electron microscope. These micrographs of the scanning microscope show randomly selected areas of a power sample, and where we take the spectra. The peaks found corresponds to characteristic X-ray of the K alpha, K beta, L alpha, and A beta transitions Then we estimate the atomic percentages from which we can determine the chemical composition. In this table, I summarize the results obtained so far, the method with the deviation, iron-manganese ratio, and composition. Then we proceed with the magnetic characterization. So to do this, we disperse particles in an epoxy resin solution. We first measure the magnetization curves as a function of temperature by applying a fixed field under the zero field code and field code protocols in an squid magnetometer. From this magnetization curves, we determine the blocking temperature distribution as shown by these red curves. From this, we find that the smallest particles, the average blocking temperature is between 5 and 15 Kelvin, and for the larger ones, it's 18 Kelvin. And on the other hand, for these nanoparticles, we estimate an irreversible temperature above 320 Kelvin. Something particular about these particles is that we observe a break around 105 Kelvin, as has been observed in other systems that go through a Berwick type transition. Then we measure the magnetization curves as a function of the field at room temperature and 5 Kelvin. For this system, it is characteristic to observe a hysteresis loop in the block regime. From this from the measurement at room temperature, for example, we find that by zooming in on the larger particles, that a small part of the system is in the block regime. Ferromagnetic resonance measurements allow to estimate the effective anisotropy at room temperature. For this measure, we dissipate particles in an epoxy resin solution and then orient them using a permanent magnet of 8,000 oyster. The strong angular dependence of the ferromagnetic resonance spectra reveal the presence of a uniaxial anisotropy in the sample. Measurements with field applied are shown parallel at 40 degrees and perpendicular with respect to the EC axis of the sample, and also show the angular dependence of the resonant field at every 10 degrees, with which Legendre polynomial has fitted, and thus we obtain the anisotropy field. Using this approximation, we arrive at the value of effective anisotropy. In this table, I summarize the results obtained from the magnetic characterization with the average blocking temperature, conductivity, magnetic saturation at 5 Kelvin and room temperature, and the anisotropy. This part is something important from the results, and the heating efficiency. To determine this, to do this, we use an alternating magnetic field, and we measure the temperature as a function of time of particles dispersed into mediums. One was hexane and the other one's clarified butteroid. From this measurement, we determine the maximum derivative with respect to time, from which we can calculate the absorption power. And in this table, I summarize the power absorption values obtained in hexane and CBO. Hexane, it's a medium where the particles are dispersed easily, but in clarified butteroid, the particles are more restricted. They can move freely in the medium. From this analysis, we find a drastic effect with the change of medium. The 28 nanometers particles that show a heating efficiency in hexane close to 500 watts per grain drops at least 7 times its value in CBO, that is clarified butteroid, while the 12 nanometers particles are initially within 50 watts per grain in hexane. They have a higher efficiency in CBO that exceeds the efficiency of larger nanoparticles. In this case, both particles could be candidates to carry out and hyperthermia treatment in cells, but it could be enough to look for nanoparticle systems that do not exceed 20 nanometers. Finally, we evaluated the toxicity of the particles in cell cultures. To do this, we grow monolayer HEP-G2 cells in six well plates and incubated them at 37 Celsius and an atmosphere of 5% of carbon dioxide. After 24 hours of incubation, we applied the doses of 30, 60, and 120 micrograms per milliliter of nanoparticles, and we incubated again for a new period of 24 hours. We performed IMTT assay to see the effect of the cell viability. These figures here show bar plots of the absorbance as a reflection of the viability as a function of those for the 12 and 28 particles. We determined that there is a considerable loss in viability with respect to the control of only in cells with doses of 120 micrograms milliliters of the 12 nanometers. In conclusion, we obtained magnetic manganese ferrite nanoparticles of 12 and 28 nanometers with low anisotropy, capable of reaching hyperthermic conditions in XN and CBO. They present low toxicity in HEP-G2 cell line and could be used to evaluate the efficiency in hyperthermia treatments. I don't know why is this occurring, but it says what I just said. Thank you for your attention, and if you have any question.
Thank you, Marco. Really nice work. I have one question. Did you use two different media? So why did you use the hexane and the butter oil?
Hexane, first, is the medium with which disperse nanoparticles to preserve them without so we can longer the duration of the phase we made, so we cannot we avoid the oxidation of the particles in hexane, for example. And the other medium, CBO, it's a medium that is more restricted. It's like, for example, we want to use particles in cells cultures, and CBO is a medium that is more consistent with the surroundings of a nanoparticle being in a cell. So hexane is a very less restricted medium. So we want to compare what is the effect of the change in medium for
to be closer to the body, right? To the organs of the body if you want to attack for cancer, right?
Yes.
Okay, thank you, Marco. We don't have any questions in the chat. Thank you for your presentation one more time. Irene made a question, like you can do it quickly. Have you checked the quantity of nanoparticle internalization into the cell?
There are more results that it is not that they are not shown here. To know the quantity of particles that have been internalized in the cells, we use thiazonide method to know how many iron 2 was remaining. Of the particles that have been internalized, it's not clear, but they are not all internalized. Some of them may remain in the membrane at the surface of the cell. So we are not so sure of the quantity of particles that have been internalized, but a quantity that we estimate from this method was like 12 picometers per cell per well.
12 picometers. Thank you, Marco.